In case of normal solutions, see, the same thing can be taken as N1V1 plus N2V2 by V1 plus V2. This is when acidic or basic. This is very important here. Either acidic or basic. Because we are adding the things. When acidic or basic solutions are mixed, need not be of the same solute. Remember. Yes. Because it's simply the equivalents that we add up. Right. Now, this is when the two solutions, of course more, are simply mixed. Now, if they are mixed and diluted to a different volume, so this is mixed and diluted case, where this V3 can be given as V1 plus V2 plus, of course, the volume of water that is being added. Okay. Next. Now a very important law called law of equivalence. See, this law says that the substrates or the substances always react in 1:1 equivalence ratio. That means, see, the number of equivalents of the first one is equal to the number of equivalents of the second one is equal to the number of equivalents of the third one. Like that, you can take any number. Okay. Now let me give you 3 different relations for calculating number of equivalents. See, number of equivalents can simply be given as weight by gram equivalent weight. Right. Next. We can also give the same as a normality into volume in liters. Now these two are from the basic formula of normality. Now this one from our previous discussion. It can be given as number of moles multiplied by n factor. Isn't it? We have seen phosphoric acid and sodium hydroxide example, in which We got the number of moles of phosphoric acid as 1, but the number of equivalents was 3 because it was 1 mole multiplied by the n factor of phosphoric acid, that is 3. So the number of equivalents can be simply given as number of moles multiplied by n factor. Now this is a very interesting relation based on which we can solve many problems. Okay. Now let us again get back to the concentration of the mixtures. Now see, this is when acidic and basic solutions are mixed. Within which we have 3 cases. See, if NaVa is equal to NbVb. Just now I told that N into V is the number of equivalents. So this can be given as the number of equivalents of acid okay, then NbVb Niket, is your video on? It's disturbing the screen. Now, see, this NbVb can be given as the number of equivalents of the base. See, because the number of equivalents of acid is equal to that of base, this can be given as a neutral solution. Okay, that is case 1. Next, if NaVa is greater than NbVb, say this can be given as acidic solution, right? Now in this case, normality of the resulting solution can be calculated as NaVa minus NbVb by Va plus Vb. Because the number of equivalents of acid is more, we are just subtracting those of the base from that of the acid. Okay, now the third case. See, if NBVB is greater than the NAVA, or of course NAVA is less when compared to NBVB, then the resultant solution will be basic in nature. Resultant normality can be calculated using this formula. No doubt the volumes are additive. We are adding the volumes. Okay. But only thing is, because we are adding acidic and basic solutions, if acid is strong, it neutralizes the base and of course will remain in the solution even after that. Likewise, in the case of basic solutions, the base neutralizes the acid. Even after that, it will be left out in the solution. Okay. Now, the next method of expressing concentration is molality. It can be given as number of gram moles of the solute present in 1 kg of solvent. Right. See the difference between molarity and molality. In both the cases, it is the number of gram moles of the solute, what we consider. In case of molarity, it is 1 liter of the solution. But in case of molality, it is 1 kg of the solvent, not the solution. Right? Now, mathematically, this can be given as small m, because molality is represented by small m. It can be given as number of moles of the solute, small n, by weight of the solvent, capital W, in kg. Okay. Now, this can of course be modified as weight of a solute by the gram molecular weight of solute. This is nothing but the number of moles into 1 by weight of solvent in kg. Or else it can be taken as weight of solute by gram molecular weight of the solute into 1000 by the weight of solvent, but in grams. See, this can also be given as, yeah, it's okay. We'll just see that later. Next. See, when percentage strength of the solution weight by weight is given, molality can be calculated using the relation percentage strength of the solution. Let this be X. See, if X% solution W by W is taken, what does that indicate? It indicates that X gram of a solute is present in 100 gram of solution. So then in this case, it will be, if the percentage strength of the solution is X, then that is going to be the weight of the solute. And in place of the weight of the solvent, we can write it as 100 minus weight of the solute, nothing but X. See, we already got this 1000 in the relation. And now it's the GMW of the solute, what is to be considered here. Of course, it's not a too much simplified formula, but based on the basic meaning of that. Okay. Now, coming to units, just like mole per liter in case of molarity, this is mole per kg. Now, coming to the effect of temperature, no, it is independent of temperature. This is an important point. Molality is independent of temperature, as it is expressed in terms of weight. And we know that weight is independent of temperature, right? Okay. Then as usual, molal are one small m solution. See, small m is nothing but number of moles of the solute by weight of the solvent in kg. Anyway, this as per the definition is 1 kg, and this we want it to be 1. So this has to be, of course, 1, isn't it? Now this can be given as 1 mole of a solute is present in 1 kg of the solvent. Likewise, we can take decimolal, semimolal, centimolal, and all the others. Okay. Now let us see the relation between molarity and molality. See, molarity can be given as weight of solute by gram molecular weight of solute into 1000 by volume of the solution in ml. Similarly, molality can be given as weight of the solute by gram molecular weight of the solute into 1000 by capital W. Okay. Now everything except the weight and volume get cancelled. See, from this it can be written as capital M by small m is equal to capital W by capital V. Right. Now capital V is the weight of the solvent, right? See, weight of the solvent is nothing but weight of solution minus weight of solute. Now this weight of solution can be given as volume of a solution multiplied by density of the solution. So let me just write this as V into D. Okay. So overall, the weight of the solvent can be written as, now this can be modified as Vd minus small w by V. Or else you can also convert this volume of the solution into weight if required. So this is the relation what we normally use. Or else, see, there is a relation which of course is derived from the same explanation. We'll see that when we go for a problem. Now it can be actually given as this. Small m, I mean molality, is equal to 1000 into capital M by 1000 into density minus m into, let me take m dash. Now this is anyway molality, this is molarity, this is density, again molarity, but m dash is the molecular weight of solute. I've taken this as m dash only to avoid confusion with the capital M or with the small m if small m is taken for solute. So I just wanted to avoid that confusion and I've taken m dash as the molecular weight of the solute. Right. So this of course can be used for solving the problems. This is about the relation between molarity and molality. Now it's mole fraction represented by chi or chi. See, mole fraction of a particular component, say the mole fraction of solute, is nothing but the number of moles of solute represented generally by small n by the total number of moles of the solute and solvent present in the solution. So this is the number of moles of solute and this capital N is the number of moles of the solvent. So that is the mole fraction of solute. Now this of course can be modified as a small w by we can take m dash by small w by m dash plus capital W by m double dash. Now here this m dash and m double dash refer to the molecular weights of solute and solvent. Only to avoid confusion with the molarity and molality, by using small m and capital M, I've used m dash and m double dash. Okay. Now coming to mole fraction of solvent. Can be given as number of moles of the solvent by the total number of moles of all the components present in the solution. So this can of course be given as capital W by m double dash by again small w by m dash plus capital W by m double dash. Okay. Now, in general, in case of a binary solution which consists of just one solute and one solvent, overall it can be given as the mole fraction of solute plus that of a solvent is equal to 1. Okay. Now, mole fraction into 100 is equal to mole percent. Next. Coming to units. See, because mole fraction is a ratio of number of moles so it has no units. Coming to the effect of temperature. No, because even the mole fraction is expressed in terms of weights of the solute and solvent, it is independent of temperature. As it is expressed in terms of weights of solute and solvent. Okay. Next. The relation between molality and mole fraction. A very important relation. Now, the mole fraction of solute can be given as small n by small n plus capital N. Similarly, mole fraction of the solvent can be given as capital N by small n plus capital N. Take the ratio of these two. Now, this can be written as small n by capital N. Small n is small w by m dash by capital N is capital W by m double dash. Even this can be written as W by m dash into m double dash by capital W. Right. Now multiplying the final relation by 1000 by m on both sides. I mean 1000 by m double dash. Okay, let's see. Mole fraction of the solute by mole fraction of the solvent into 1000 by m double dash is equal to small w by m dash into m double dash by capital W into 1000 by m double dash. Right. Now these two get cancelled. And the thing that is left out, just check this out. Weight of the solute by gram molecular weight of the solute into 1000 by weight of the solvent. What is that? Nothing but our molality. So this is molality. Molality, of course, is equal to this same relation. Now this is an important one. Mole fraction of solute by mole fraction of solvent into 1000 by m double dash is equal to molality. Or else I have another relation. Yes. It goes this way. Mole fraction of the solute is equal to molality by molality plus 1000 by m double dash. The small m here, remember it refers to molality. M dash, I mean m double dash, this of course is as usual the molecular weight of solvent. Okay, so this is the relation. Of course, this can be explained by, this can be explained on the basis of the same discussion. We'll see that when we go for problem solving. Okay, so this is the relation between molality and mole fraction.